Hello everyone, welcome back again in the course of higher surveying, and today we are in the new module, module 5, Global Positioning System. Today you might be excited also because we are going to talk about GPS, which is a first relevant topic. And before whatever we have covered, for example, module 2, which was about reference frame and coordinate system, module 3 about astronomy and time, and module 4 about the adjustments computation and error propagation, accuracy, error, precision. You might be asking that why did we cover 4 modules, almost 14 to 15 lectures before we start today's lecture. Let me tell you very clearly and categorically, first 4 modules are the basic fundamental tools, or they are the relevant concepts without which you cannot work or you cannot understand any topic of higher surveying. For example, if I take the module 2 about reference system and coordinate system, reference systems are very useful to understand what is geocentric coordinate system, or what is a geodetic coordinate system, what is a local reference frame. Later, we have also talked about astronomy and time. We have talked about the time, like how to measure the time, what do you mean by time, what is atomic clock, what is atomic time, ephemeris time, what is rotational time of Earth, and so on. And we also defined sidereal time, that is related to the orbit as well as spin time of Earth. Then we talked about astronomy. So we locate the 2D position of a star globally, locally. Locally we have said azimuth and altitude. Globally we have said declination and right ascension. We have established the relationship between the ITRF and the ICRF. Remember, ITRF we learned in the module 2, reference frame and coordinate system. ICRF we learned in module 3, in time and astronomy. In module 4, we talked about what is accuracy, precision, what are the measures of accuracy and precision, and how to do adjustment computations to find out the errors and accuracy, and how to do error propagation to find out the precision in the dependent variable. Now, how to use these concepts in today's lecture? Let us see, and you will appreciate that whatever tool we have learned in last 4 modules, they are very, very useful for development of your concepts about GPS and other technologies like photogrammetry, radar, lidar, bathymetry, and so on. Okay. So let us dive into today's lecture, that is Global Positioning System, and I should have coined this term as GNSS, which is Global Navigation Satellite Systems, because GPS is the term generally used for Navistar satellite configuration. What is that? Navstar or GLONASS or Galileo, what is that? We are going to discuss today everything. Moreover, this module or this lecture, it is more about the information that you perhaps need, but you are not aware of that. The basic fundamental knowledge of the GPS, please refer NPTEL course on basic surveying. Fundamentals are relevant as well as applicable here also. So I am assuming that these are the prerequisites for this module or for this lecture. So with this idea, I am going ahead now. Okay, so these are the books. These 3 books are fundamentals books. This is slightly different book. It has slightly different taste or different flavor on the material, but still it's a relevant book. These 2 books are more on technical side. So if you are electrical engineer interested in the mathematical treatment of the signals, you can refer these 2 books, but first 4 books are good enough for any serious learner from the civil engineering perspective. That means topographic mapping only. Now we have satellite orbits. So in general, satellites are placed in 3 types of orbits, and then we name them accordingly. So first is low Earth orbit, or in bracket it is written LEO, right? If you just try to see sometimes in the sky, and by accident if you come to know that there is a star which is continuously moving, probably it is a LEO satellite. Moreover, please differentiate between aeroplane that appears quite big compared to the star. A star appears like a dot in the sky. So if you are seeing this dot moving in the sky in the night time, perhaps you are looking at a LEO satellite. You can see with the naked eyes. All the spy satellites, for example, Corona or Lanyard or Argon, all these early spy satellite programs, they were using LEO orbits, and the range of the LEO orbits is less than 1000 kilometers above the surface of Earth. So, for example, Corona was placed around 150 to 215 or 225 kilometer range, and they were acquiring panoramic images of Earth. Later on, when remote sensing was started, so nowadays remote sensing satellites are placed somewhere around 750 to 900 kilometer range. So they are also LEO satellites. All the weather satellites reporting the weather, they are also placed in the LEO orbits. Next is the MEO satellites, or the medium Earth orbit, and the orbit is around 22,000 kilometers above the surface of Earth. Most of the GNSS satellites are placed in the MEO orbits. What is the GNSS? Global Navigation Satellite Systems. GNSS is a generic term that includes all the possible satellite constellations. GPS is, or Navistar is one of the satellite constellation launched by the USA or developed by the USA. Apart from that, most of the countries like India, they have also developed their own satellite constellation to serve their nation. These orbits are inclined with respect to the equator of the Earth, and orbital period defined in sidereal days. That means how many sidereal days a satellite is taking to complete the orbit around Earth. Then we have third type of orbits called geosynchronous Earth orbit, we call it GSO, and geostationary Earth orbit called GEO. Okay, let me differentiate between the two, GSO and GEO orbits. GEO is geostationary Earth orbit. They are generally placed on the equator. That means in the equatorial plane at this height of 35,000 to 36,000 distance from the surface of Earth, they are revolving around Earth. So let us say this is equatorial plane of the Earth. So somewhere it is 35,000 distance, and satellite is orbiting in this plane of equator or equatorial plane, or you can say celestial equator plane. So these are called GEO satellites, or it's called GEO orbit. Fine. Generally, they revolve around the Earth in the same direction of the Earth's rotation, that is anticlockwise. Then we have geosynchronous Earth orbit. If I place the same orbit at 35,000 height above the surface of Earth, and in this inclined plane like this, or it could be like this, and let's say this is equatorial plane. So these orbits are called geosynchronous orbits. So what's the purpose of geosynchronous or geostationary Earth orbit? Well, these satellites, which are placed at almost 35,000 kilometer height, they remain fixed with the Earth. That means when they are projected or when they are placed at a certain point with respect to Earth, then they will remain over that always. Why? Because they are rotating with the speed of the Earth, which means they are completing their one revolution or one orbit around Earth in one sidereal day. And that's why they are called synchronizing with the Earth, geosynchronous satellites, or geostationary. They remain stationary with respect to the Earth. But geostationary are placed in the equatorial plane. Geosynchronous are placed in the some inclined plane. So we have two kind of now satellites, geosynchronous, geostationary. Remember, both revolve around the Earth with the same speed of the Earth, and that's why they are named geostationary or geosynchronous. All the communication satellites, like for example that used for the mobile phones or TV satellites, television, they are placed in the geostationary orbit, and some of the GNSS satellites are placed in the geosynchronous orbits also. Now I am trying to define what do you mean by an orbit or orbital plane of satellite. Let us see, this is one orbit here. This is the inclination of orbit. You can see here the capital XYZ is a geocentric reference frame. This capital XYZ is ITRF, International Terrestrial Reference Frame. Secondly, we associate ellipsoid with this reference frame. For example, for GPS we associate WGS84 ellipsoid, right? So the moment there is a association of the two, one is reference frame which is geocentric in nature, and then we have ellipsoid. So I got a datum surface with respect to which I can refer the heights, what we call ellipsoidal heights. So I will use that ellipsoid for measuring the ellipsoidal height. And GPS is going to use that particular ellipsoid in order to report the ellipsoidal heights, right? So that's the purpose here, to associate two things. This is one of the orbit of the satellite here. This is the inclination angle, what we have seen here. So now I can see that all the satellites are moving, let us say, in this orbit. Like this, there are 4 satellites moving in this orbit, and so they are maintaining some speed, and as a result they are not colliding with each other. Rather, they are moving at a constant speed with each other. And what's the order of the speed? The order of the speed of satellite is in the kilometers per second, right? With this idea, you can imagine that for these 4 satellites, this is the one orbital plane, and rather these 4 satellites are assigned to this particular orbit, and they are moving always in this orbit. Let us take another orbit. This is another orbit, and what is the inclination of this orbit? So if I measure the angle of this orbit with the equator, that is called inclination. So let us see. This is the angle I for this orbit, because it is inclined with respect to the equatorial plane at angle I. So that is called inclination. Now you can imagine there are 2 orbits like this, right? It could be another orbit like this. It could be another orbit like this. Fine. So you can imagine that at a given inclination I angle, I can have these many orbits, which are, let us say, this is orbit. So this can be this orbit, orbital plane like this. This can be this way also. This can be this also, like this, and this can be this also, like this, orbital plane. So basically, this orbital plane is making an angle I with respect to the equatorial plane, and that's why all these are different orbits, but they are having the same inclination. There are 4 satellites placed in the particular orbit having inclination I. Now, have you ever thought how coordinates of satellites are available to us? Because if you can recall the fundamental concepts of the GPS from the basic surveying course, then you will realize one thing. We need to first have the coordinate XYZ of satellite. Using that coordinate XYZ, we try to find out the receiver's coordinate XYZ. And how do we do? We have this XYZ available to us. Then we measure the distance by the time difference or maybe phase difference logic between the receiver and the satellite. And then using this two information, distance and the coordinate of the satellites, we find out the location of the receiver by space resection. Well, that was the idea I've already learned in the basic surveying. Right. So we assume that satellite coordinates XYZ are available in geocentric coordinate system. So let us say that geocentric coordinate system is XYZ. It could be ITRF. Then we have a orbit shown here, and what are the characteristics of the orbit that remain same for all the satellites moving in that same orbit? That we try to learn now. So let us see, this is a satellite here, and if I connect the center of the Earth to this point where the orbit intersecting with the equatorial plane, we call it node, right? This is the inclination angle as explained in the previous slide. This blue line here is indicating semi-major axis small a. We define this angle omega, that is the angle between this line which is connecting the center of the Earth to the node and the semi-major axis. So this angle omega is defined in the orbital plane of satellite. This is called argument of perigee. What is the meaning of perigee? Perigee is the point on the orbit which is nearest to the Earth. So when we talked about the orbit of the Earth around Sun, we defined apogee and perigee points for the Earth. Similarly, we are defining here perigee point for the satellite revolving around the Earth. So this is orbital plane where it is supposed to revolve. Now this angle, the right ascension of ascending node. So this node is ascending node because satellites will be ascending from this node. So ITR is giving a 0 degree longitude by x-axis. So that's why we are measuring the right ascension of the node like this. This is the coordinate system, small xyz like this, and this small xyz is an orbital plane. That means x and y are aligned with the orbital plane. Z-axis is perpendicular to the orbital plane. Let us look into the motion of the satellite moving in the orbital plane. So now you can see that since satellite is moving in the orbital plane, it is changing its coordinate in the orbital plane, but the z coordinate is 0 because small xy coordinate system is defined in the orbital plane. You can easily imagine that if I measure the time, so with respect to time, satellite is changing its position only in the orbital plane, right? So I can always define the position in the 2 dimension. I need not to define in 3 dimension because the small z, the z dimension in orbital plane or with respect to orbital plane or with respect to small xyz coordinate system is 0. And let us say this is the radius r or the radial location of the satellite. This is the point of satellite which we are indicating that this is the CG of the satellite. So let us remove the satellite and talk about the point. So this is the point indicating the satellite here, red dot. This is the radius. So as satellite is moving, this r variable will keep on changing. Here I need to define the position of satellite by one more coordinate so that I can fix its location anywhere in the orbit. So this angle called true anomaly mu. So this is the variable that is fixing the 2D location of the satellite in the orbital plane. Now using these 2 variables r and mu, I can define any position in a satellite orbit. So I can write r here like this. So this is eccentricity of the elliptical orbit which is close to the circular orbit. It is representing a position of the satellite. Okay, what about x, which is from this point center of earth to this point here? So this is r cos mu, you can see Cartesian coordinate system, and this is y, which is the perpendicular distance from x in the small y direction. So these 2 are already given here. Now I can express the position of the satellite like this 3 coordinates. Remember, third coordinate is 0, small z axis. We have defined the position of a satellite in orbital plane. Now we know that there are 2 coordinate system, one is small xyz and another is capital XYZ, and capital XYZ is the WGS84. So I have expressed the position of satellite in orbital plane, and I want to calculate the position of satellite in the capital XYZ system or reference frame. So let us see, we need to do some rotations only because both systems are geocentric, and as a result I need not to do any translation there. Their origins are basically coinciding with each other. There are only difference of orientations. So I can write like this, where r is rotation matrix, or the xyz of the satellite is equal to r times xy0. I will rotate small xyz system around z axis such that this x axis will be aligned with this line. So let us see what kind of rotation we do. This rotation, now it is aligned, and I have rotated this system about z axis, so there is no change in the z value of the satellite coordinates. Okay, so now just think that if you rotate about this new axis, say x1, right, and it is new axis called y1, and z is still z. So about x1, if you give another rotation by angle I, remember this omega direction, it is in the clockwise direction, so we have written minus omega. Now you are rotating new coordinate system x1, y1, z about x1 axis, so that z and y1 will rotate and they will come into the plane of equator by I angle rotation. Let us see. So this is explained like this. This kind of rotation we are doing now. Done. Remember that we have not changed the orbital plane of the satellite, just for the purpose of explanation we are showing it by animation. Okay, you have rotated by minus I also about the x axis, which was this, like this kind of rotation you have given, right, and as a result z has aligned with the capital Z. Now still these small are marked here, they are of no use. This is new z1 axis, small z1, and this is y2 axis. Only I need to give one more rotation so that this axis, that is x1, will be aligned with the capital X, and this rotation is required here, which is equal to this. and again in the negative direction, because we are going to rotate now about z axis in the clockwise direction. See how do we do it? Like this. So now x1 axis, which was here earlier, is now aligned with the capital X here after rotation by this angle. So small xyz system is now completely aligned with the capital XYZ. So whatever coordinates I have transformed now, I can measure this position in the capital XYZ. Again, we have used the logic of coordinate transformation, and that's the reason whatever we have talked in module 2 was relevant. If we place this rotation matrix here and I place these values here, I will get the coordinates of satellite in WGS84 geocentric reference frame. So here I said that it is ITRF. So you got how to calculate the position of the satellite in a geocentric coordinate system when it measures r and mu in the orbital plane. So let us have the brief overview of the GNSS now. What is GNSS? Global Navigation Satellite System. These are the various constellations available, and they are countrywide. For example, Navistar, what we call GPS, is navigation, satellite and ranging, and developed by the USA Department of Defense initially for the purpose of military use. However, it is now more popular for the civilians. Second is the GLONASS, that stands for Global Navigation Satellite System, and it is developed by the Russia. Okay. Third is the Galileo. We have for India, Indian Regional Navigation Satellite System, IRNSS. For Japan, they have Quasi-Zenith Satellite System, and for China, we have BeiDou or COMPASS. Well, earlier we have only GPS developed by the USA. These countries have developed their own systems now. First is Navistar. Okay, there are minimum 24 satellites. Nowadays, we have 30 satellites in the Navistar or GPS. So these 30 satellites are placed in the 6 MEO orbits at the height of approximately 20,200, and each orbit is inclined at 55 degrees. So now you can place all these orbits with respect to each other like this, but they are basically inclined at 55 degrees with respect to the equator of the Earth. Okay, what about the orbital period? That means each satellite is completing one orbit in half sidereal day. That means each satellite is making 2 orbits in a 1 sidereal day around the Earth, right? That means when it starts from one position, in half a day it completes 1 orbit, in remaining half day it completes 1 more orbit. What about the footprint of satellite? It creates vertical S shape. Then we have this frequency L1, L2. Well, these two are already discussed in the basic surveying course. Then we have L5, one more frequency now for the civilian use. They have this codes, CA code, P code, and then we have different combinations of the code and the frequencies which are available for the use or for the receiver to receive it. Okay, so let us go ahead and see what is the vertical S shape. This is the shape of the Earth shown here, and if I try to make the 55-degree lines, that is 55 degree north approximately, and this is 55 degrees south. The satellite is moving in elliptical orbit or in the inclined orbit. So when satellite goes up above equator, it is going to rise, its footprint or its track on the Earth is going to increase. It will go maximum to 55 degrees, that is inclination of this orbit, and then it will start moving down. So that kind of pattern we should expect on the surface of the Earth, or rather if I draw on the plane, this pattern will be somehow like this, a kind of S pattern, this way and so on. It will keep on repeating. Next is the Galileo, which is very similar to the GPS, and it has total 30 satellites, and they are placed in 3 orbits of this height, which is slightly above the GPS satellites. And again, the inclination is more or less same, so it is going to create more or less same as that of the GPS satellites. In each orbit we have 10 satellites, and what is the orbital period? It's written 10 by 1 here, which means they complete 10 orbits in 1 sidereal day. GPS satellites complete 2 orbits in 1 sidereal day, but they complete 10 orbits in 1 sidereal day. Okay, so again vertical S shape will be created, and then they have 3 signals called E1, which is same as L1. Again they have E5, which is same as L5. Then they have E6, which is different here. Right, so they have 3 frequencies, and These signals, although they are on L1, L5, but they do not interfere with the GPS signals. Okay, so I am not drawing vertical S path, which is similar to the GPS. So let us talk about GLONASS for Russia. In this constellation, we have total 24 satellites. They are placed in the 3 orbits, almost at this height, 19,100 kilometers, which is different from GPS as well as Galileo. Galileo is slightly higher than the GPS, and GLONASS is slightly lower than the GPS, but all are MEO orbits. Okay, and they are inclined at 66 degree. So you will be surprised why 66 degree, whereas GPS and Galileo they are around 55 degrees or 56 degrees. The latitude of the Russia is around 66 degree. So is it a kind of global system or it's a local system? We call it as a regional system. They are basically targeted or tailored, or basically they are tuned to serve the particular territory on the earth. So each of these systems what we are talking about now are basically the regional systems, or we can say regional GPS. These are the regional systems, but does it mean that others cannot use, or the people of one region can only use? No, it's not like that. If you are having a receiver which can acquire the data of particular satellite constellation, for example GLONASS or Galileo, you can also use it. Next is the orbital period, which is 8 by 17. What does it mean? They finish the 17 orbits in 8 sidereal days. If I take the ratio like this, 17 by 8, so orbital period will be more than 2, right? So that means they are completing more than 2 orbits in one sidereal day. And that's the reason in order to give the integer number, we have expressed like this. That means they are covering 17 orbits in 8 sidereal days. So after 8 sidereal days, satellite have completed its 17 orbits around Earth, and again the point where it started above the Earth and the point where it's completed, both are coinciding after 17 orbits or after 8 sidereal days. Okay, what are the frequencies? It uses 14 different frequencies. Remember, GPS is using L1, L5 and L2, 3 frequencies, but they use different frequency. On the other hand, they use only one PRN code. GPS is using 2 or 3 codes, CA code, P code, and maybe Y code also, which is not available for the civilians. It is for military only, but still using 3 codes. However, the GLONASS is using only one PRN code, but different frequencies for 24 satellites. And then we have opposite satellites across Earth uses the same frequency. This is a specification of this system. Let us define the 66 degree line. So this is approximately 66 degree north, and this is 66 degree south. And Russia is somewhere here. If I try to draw the track of the satellite on Earth, it will be something like this, and so on. It will complete 17 such tracks in 8 days. Well, that's the idea here. Okay, now we have the quasi-zenith satellite system, which is developed by Japan. So it has total 7 satellites. So we have 4 geosynchronous satellites and 3 geostationary satellites here over Japan, and 4 satellites are placed in one geosynchronous orbit, which is of this eccentricity. Yes, eccentricity is very important because most of the satellites are using close to circular orbit, or we can say eccentricity is in the order of 10 to the power minus 3, 0.004, 0.001, something like that. But it has very high eccentricity, and that has very special use here. The idea is that Japan is a very small country, and they want to use this QZSS very precisely all around their country. Specifically, they are not restricting anyone to use it, but still they would like to use it more specifically over their territory, and that's why they have designed their system like that. So it has one orbit of this height, and these satellites are inclined at 41, or these orbits are inclined at 41 degrees, because that is the latitude of the Japan. Number of satellites in geosynchronous orbit is 4, and number of satellites in geostationary orbit is 3, that is in the equator plane, that is 0 degree inclination, and there 41 degree inclination. Okay, what is orbital period? 1 orbit in 1 sidereal day. What is the footprint? It creates kind of small lobe over Japan, and then they have these signals L1C, L1CA, L2C, L5, L6, or LEX. It's also called LEX, that is L1 experimental. They have some different signals, which is slightly different from the GPS. But L1, L2, and L5 are same. Again, signals do not interfere. So let us draw the 41-degree line like this, and this is 41 degree approximately. It is around 41 degree north. So now if I define a box, because it is creating the lobe of 8. So here if I draw some figure, so that will be like this kind of 8 over the Japan here, and then it will be big lobe over part of the Australia, and like this, the track of the satellite. And that's the reason that eccentricity of 0.075 is designed. The Indian Regional Navigation Satellite System, it has total 8 satellites, right? I have taken the recent update from the website of ISRO, and there they have placed 5 geosynchronous satellites and 3 geostationary satellites over India. It has certain longitude, so these satellites are moving exactly over the particular point on the Indian territory. So 5 satellites are placed in 2 geosynchronous orbits. It creates symmetric circular orbit and 2 symmetric figures of 8 as footprint of satellite on Earth, especially around India, not exactly over the India. Okay, so there are 2 orbits as we showed here, and these 2 orbits are at this height and inclined at 29 degree. Again, this is the kind of latitude India has, or most of the part of the India is around this latitude. So all the systems are now regional GPS or the regional GNSS. Well, still they are global because anyone can use across the world. Let us see, these are the 5 satellites, right? And these names are INSS 1A, 1B, 1D, 1E, and 1I. In these geostationary orbits, we have 3, 1C, 1F, 1G. 1H is somehow could not be placed, rather it is a kind of lost, or well, it's a failed mission. So we have total 3. What about the orbital period? We have 1 sidereal day, so 1 orbit in 1 sidereal day. Remember, it's a geostationary, so it is going to create 1 orbit in that height of 35,000 kilometers. So we have signals on the S band, which is called 2492 megahertz, and we have also L5. See, it is quite different from the other satellite constellations. Now, these lines which we place here, it is 29 degrees north. Similarly, this line is around 29 degree south. Well, okay, now what about the shape of 8? The shape of 8 is created by the satellite tracks in this way. One like this, and another is like this. So these are the shape of the 8, and this is equator position. So we are having 2 shape of 8s, that is satellite tracks around India. Last is the BeiDou, developed by the China. So it has 35 total satellites and 3 geosynchronous satellites GSO, 5 geostationary, and 27 MEO satellites. These 5 satellites here are placed in 2 orbits. Then it has symmetric circular orbit because its eccentricity is 0.004, which is very close to the circle, or circle has eccentricity of 0. It creates a symmetric figure of 8 at footprint over China region, and then it has geosatellites at a height of this and inclined at 0 degree, that is a geostationary. So this is their longitude range. That means over these longitudes, these orbits are placed in the geostationary form. So satellites are basically moving at some longitude permanently. It will appear like that. So then orbit of GSO satellites are 3 orbits at this height and inclined at 55 degrees. Fine. It has MEO satellites also, 3 orbits and the 21,528, which is slightly lower than the GPS, and they are inclined at 55 degrees. Well, what about the orbital period? More than half a sidereal period, more than that. So 12 hours 53 minutes, almost we can say 13 hours of sidereal day, right? And then it has 3 signal frequencies, B1, B2, B3. These 2 lines at 55 degrees north and 55 degrees south. This is the box here. So if I create the shape of 8, so it will be like this. shape will be somehow like this. I am trying to draw a appropriate shape. Well, so that's the idea here. So this is the Chinese region here. So all these are regional GPS systems, or we can say all are global in nature. However, they are tuned for regional requirements. Now we have learned about all the GNSS constellations. So let us try to look into the specifications of GPS receivers that you may buy or you are planning to buy. These are very common specifications: number of channels, position accuracy, data logging rate and data output rate, data storage, data delivery format, data post processing, and then special features. They are provided by the manufacturers in the GPS machines. So start with number of channels. What do you mean by number of channels? If I take the number of satellites, say 30 for GPS, and all these are signals, L1CA, L1C, L2C, L2P, and L5, right? They are available for the civilians. And if I say this 1, 2, 3, 4, 5 signals and 30 satellites. So if I multiply the 2, because each satellite is transmitting the signals on these 5 frequencies and code. So they have 30 satellites, we have 5 such signals, so 30 into 5, 150. In the same fashion, if I take these as the number of satellites which are in the operation, and if I multiply with number of signals each satellite is transmitting, let's say 5 here again, then we'll get 120 here. Similarly for Galileo, 30 and 1, 2, 3, 4, 5, 6. So I got something this figure. This could be wrong slightly, right? QZSS 7, then we have something this kind of number. So I got 35. Here 28 satellites for Beidou, then 3 frequencies or 3 signals. So we have total 84 here. And for IRNSS, not mentioned in the specifications of GPS machines or GPS receivers. So if you make the total of this thing, it will come close to 570, just try to calculate it. We have the different combinations. Some specifications say 120 channel, some says 220 channels, some says 440 channels, and the maximum is this channels. So I have shown the calculation for these maximum number of channel. Maybe I could have missed some satellite number, or I could have placed little more satellites and maybe little more signals, whatever. But yes, while you purchase a GPS receiver of high quality, of geodetic quality or mapping quality, where you expect millimeter level accuracy, you should first ask your vendor what's the meaning of channels. If he is aware of that, he will definitely explain you this calculation. But be sure what you are purchasing, right? Next, DGPS accuracy. What is that? If we use the code based and still we use the DGPS, that is differential global positioning system, that means I have a rover and I have a base. I am processing the data of the two, but I am calculating the position of the rover. This is my rover, say this pen, with respect to a base which is fixed in location, and rover is moving all around in within some range 30 kilometers or whatever is specified by the manufacturer of the GPS receiver. So this accuracy in the code based in the DGPS mode is around 0.25 meter. It is not frequency receiver. It is just the accuracy of the code. So that's the meaning here. All these accuracies of the DGPS or GPS are specified in the geocentric system, not on the local reference frame on the surface of Earth. Be careful on this part. So how can you verify it? We'll see some method today. What about the RTK performance, real-time kinematic? That means you have a radio modem on the rover and there is a radio transmitter on the base, and transmitter is sending, or the base is sending the corrections in the real time to the rover, and rover is finding out its position. Well, in this we have some accuracy specified. Further, in the static performance, I am collecting the data at rover as well as base, and later on I am processing the data in the laboratory after the mission is over. That is, data collection is over, then I am bringing the data of the base as well as rover and I am processing in the software. And that is called the post processing. After the mission I am processing the data, and that is called static performance or the accuracy for the static. Static is no doubt higher. RTK is also considerably good because RTK accuracies are in general in the range of 8 mm plus minus some ppm, right? Similarly, static is around now 3 mm to 5 mm. They have specified also all these accuracies in vertical accuracy form, horizontal accuracy, accuracy in the geocentric coordinate system, not in the local reference frame. So don't get confused. Or the accuracies are not in the map projection system. No, they are in the geocentric coordinate system, capital XYZ, ITRF. Sometimes they specified confidence level also, and some of these specifications are saying now this kind of confidence level, which means if I take the position using GPS machine, I may get this kind of position. If I take multiple measurements in this given accuracy of 8 mm or 3 mm or whatever, if I draw a circle here like this, 99.9% data will be within this 8 mm. Say if I am referring this kind of accuracy, or within this 3 mm whatever. So that's the meaning here. Remember, these accuracies are specified again in geocentric coordinate system, not in the local reference frame. So with respect to the equator, I should measure planimetric accuracy, and perpendicular to equatorial plane, I should measure vertical accuracy. If you can observe, there is thumb rule that vertical accuracy is almost 2 times of the horizontal accuracy, and this is the reason. The reason is that satellite is moving above the equator, below the equator like this, and here it is moving all around, all the satellites. So I have horizontal positions calculated from all around these satellite positions. However, vertical position is always calculated if satellite is above the horizon, or I can say with respect to horizon, if satellite is above, then it can be useful for position calculation. However, a satellite which is below horizon will not be used. So I can say the half of the satellites are not available at a time, but for horizontal positioning, all the satellites are available. Or that's the reason vertical accuracy is inferior to the horizontal accuracy, and the ratio is 2 times. So if you have 8 mm horizontal accuracy, you will observe vertical accuracy will be 15 mm or 16 mm, something like this. Now data logging rate. These are the rates are available nowadays in the specifications. That means they are recording 20 data per second, that is 20 hertz, 5 data per second, and you can do this setting while controlling the receiver. Data output rate, once you take the data from the receiver, at what rate it will be transferred. Now that is not very important, because anyhow you will transfer the data, whether it will take 1 minute or it will take half a second, you will transfer it anyhow. Data storage, they have the internal memory to store the data. That means the moment data is collected, it immediately is stored in the internal memory in the receiver itself. Other arrangement is SD card. You can apply the card. Well, SD card could be a very high capacity, but internal memory is favorable. Why? Because it takes less time to store the data. It's kind of RAM. Internal memory is RAM, and SD card is kind of hard disk that you apply from outside. So transferring the data from the machine to internal memory is much faster than to transfer the SD card. Next, data delivery format. Okay, once the data is recorded, most of the manufacturers prefer to record in the proprietary format. Why? Because then they will use their software to transfer the data into the universal format called RINEX. So it's kind of developing a proprietariness on their data, or they are saying that we have our proprietary, but some of the manufacturers are now providing data in RINEX format. That means you are free to use any free software for data processing. Well, data processing, that data can be processed through software, that means in the post-processing manner, or it can be processed in the hardware also. These facilities are also available. That means whatever data you are collecting, it is directly processed immediately there itself in the hardware of GPS receiver itself. And once you take the data out, it is delivered you in the direct answer form. So there are some special features. First is the battery. Nowadays they have hot swappable batteries, which means there are 2 batteries in place, but one battery at a time can be charged and one battery will be in service. So now you realize, let's say you place 2 batteries, both are working. So one battery is being used by the GPS receiver and one is a spare in the box itself, in the receiver itself. Now the moment that particular battery which is being used is discharged, it will give you an indication. So what will you do now? You will remove this battery and automatically receiver starts using the another battery. Okay, what's the advantage? Now you can charge this battery which you removed, and then once after 2 hours it is charged, again you replace this battery and you can check the status of the another battery which is being used. So this feature is called hot swappable batteries. Okay, what about data transfer? Data transfer can be done by Bluetooth or even with your helping GSM. You can put a SIM inside the GPS receiver, and using that SIM, it can communicate to your mobile, or you can transfer by email also, right? So that's somehow an advantage now. What about the radio modem? They have internal radio modem as well as external radio modem. For external radio modem, you need to pay a little extra. Nowadays, internal modems are also coming for RTK facility. But remember, in India, transmitting the radio frequencies are denied. Then we have facility called tilt sensor. This tilt sensor means, suppose you are using the GPS or the DGPS on your boat, and boat is moving on a water surface, so it is kind of tilt is there. Tilt sensor make the measurement of tilt, and it will provide you the tilt correction. So if you read this tilt sensor, understand that is the purpose. Then we have operating temperature. Generally they specify minimum to maximum, while these days range is somehow around -20 degree or maybe -30 degree to +55 degrees centigrade. That means you can go in desert where temperature could rise around 50 degrees and you can work with your DGPS machine, or you can go to the glaciers where temperature is sub-zero, even up to -10 degrees centigrade or -20 degrees centigrade, your GPS machine will work there. Okay. So what about the accuracy? Suppose you have ordered one DGPS and you want to verify your accuracy. So what will you do now? So we have devised a simple way, rather we are suggesting. So let us say there is a line AB, and now you will collect the position using your DGPS or GPS over these points. Let us say 10 points you have placed like this. That means you have placed your DGPS machine here, here, and so on. Then you will calculate the position. Let's say positions are like this. So what will you do now? You will first take an arbitrary position, say this by DGPS. This is your reference point. Let us say this is x0, y0, z0 coordinate. Bring coordinate system from geocentric coordinate system to the local terrestrial frame. You assume that this location, which you do not know truly, but you say that this is an arbitrary reference position. Okay, now let us say this is x1, y1, z1 position. Fine. Find out difference. That means what's the length of this vector, like this. Similarly, you can also do one thing. You will orient total station in the local terrestrial frame, and local terrestrial frame is designed with the help of this point. With the help of DGPS, you can take another point here, let us say x0 dash, y0 dash, z0 dash, and then you can find out the bearing of this line and put total station here now. Using the bearing of this line for the referencing of total station, you can find out what is location of green dot and try to find out the accuracy between the two, red dot and green dot, right? So that is calculated by GPS or DGPS, and that position is calculated by total station. In the same reference frame, you find out all these accuracies like this, or maybe this accuracy. Well, that's the idea here. Now you can use the RMSE calculation also, that is, one is reference and one is observed. So this is your observed, and position of this by total station, which is, let's say, 3 mm accurate, it becomes reference. And if there are n number of points, then you use this formula to find out the RMSE and check whatever claim has been made by the manufacturer are true or not. And then you can find out whatever requirements you have about accuracy, whether these accuracy figures are fulfilling those requirements or not. I hope that this lecture was very, very informative for you. If you want to read more on the applications of the GPS, then you can go through these two papers. They are available free on the internet, and you will be enormously benefited if you go through these two. So we will meet in the next module on photogrammetry in next lecture. Thank you very much.